Hi, welcome to BC Video 9.2a Part 2, Convergent and Divergent Series. Be responsible for that. Okay, I have created a worksheet for you that I'm posting. Worksheet 9.2 and 9.3. So these are a few things that the book just doesn't have. It has the answers down there as well. So we're looking at 9.2. Now there's two different parts to this question. We're actually going to do the second part first. So the second part says determine if the infinite series is convergent or divergent. It really should say determine if the corresponding infinite series is, because the first thing they want you to do is write with sigma notation the infinite series that is the given sequence of partial sums. So you'll notice they're giving you a sequence of partial sums. First part, they're asking you to just come up with the corresponding series, and then once you've got the series, decide if it's convergent or divergent. We're actually going to do that in reverse. We're going to be able to decide if this unknown corresponding series is convergent or divergent, and then I'll show you a way to actually come up with the formula for that series. Please note 9.3, these questions will be for the next section. Okay, so we're going to start with determine if the series is convergent or divergent, and that's using what we had right here on the previous page, which is if you find the limit as n goes to infinity of Sn, and you find that that converges to a number, then your series converges to that number. If it diverges, then your series diverges. Okay? So we're going to find the limit as n goes to infinity of our Sn, which is n squared over n plus 1. Turns out that that's infinity. Therefore, the sequence of partial sums diverges, hence the corresponding series, which we haven't found yet, also diverges. If we look at number 12, we have the limit as n goes to infinity of 3 to the infinity, which is infinity. Again, since the sequence of partial sums diverges, the series will also diverge. Now, to answer the first part of the question, which is to go from the formula for the sequence of partial sums to the formula for the series, the corresponding series, this is not in the book, so make sure you know this formula. The an, which we're looking for, is going to be the Sn, which we were given, minus S of n minus 1. Now, this shouldn't be too hard to understand, because if the sum of the first four terms, of course, is a1 plus a2 plus a3 plus a4, and the sum of the first three terms is, of course, a1 plus a2 plus a3, if I take the sum of the first four terms and subtract from it the sum of the first three terms, surprise, surprise, you get the fourth term. So an equals Sn minus Sn minus 1. So if we go back to our number 10, the Sn was n squared over n plus 1. Our an is Sn minus Sn minus 1, which is n squared over n plus 1 minus n minus 1 squared over n minus 1 plus 1, which of course is n. And then you're going to find a common denominator, blah, 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 blah. Okay? And you end up with this expression right here. Now, at this point, we think the series is summation n goes from 1 to infinity of this expression, but you have got to check the first or possibly the first two terms. So the sum of the first one terms should be equal to a1, right? The first term, that's what the sum of the first one terms is. So S1 is 1 squared over 1 plus 1, which is a half, and according to our formula, a1 would be 1 plus 1 minus 1, which is 1 over 1 plus 1, which is a half. As long as the first term works, you don't have to check any others, and our series is summation n goes from 1 to infinity of that expression. If the first term does not work, but the second one does, you'll actually write the first term plus summation n goes from 2 to infinity. We talked about this. If the limit of the sequence of partial sums equals a particular number, the corresponding series converges to that number. Here's us changing our Sn into an, find the corresponding series for the given sequence of partial sums. So there's that formula, an equals Sn minus Sn minus 1, which in our case is 3 to the n minus 3 to the n minus 1. Now this is a bit tricky. I am factoring out. If you think about when you factor x to the fifth minus x squared, you factor out the common factor to its smallest exponent. So if you look at these two exponents, the smallest one is n minus 1. So if I factor that out, 3 to the n minus 1 times 3 to the 1 would give 3 to the n, minus 3 to the n minus 1 times 1 gives 3 to the n minus 1. Well, of course, 3 minus 1 is just 2. So we get an equals 2 times 3 to the n minus 1. Now we've got to check the terms, okay? So we'll start by checking the first term. The sum of the first one terms should equal the first term. The sum of the first one terms is 3 to the 1, which is 3. The first term, according to us, our formula that we got, is 2 times 3 to the 1 minus 1, which ends up being 2 times 3 to the 0, which is 2 times 1, which is 2, and that is not correct. So we are going to have to pull that first term out. Now we're going to try the second term. So the sum of the first two terms should equal the sum of the first one terms plus the second term. The sum of the first two terms, according to our formula, is 3 to the 2. The sum of the first one terms is 3 to the 1. The second term, according to our formula, is 2 times 3 to the 2 minus 1, which is 6. And that means, does 9 equal 9? The answer is yes. So it was only the first term that didn't work. The correct first term comes from the sequence of partial sums. It is 3. And then plus summation n goes from 2, be careful, to infinity.